substitution, and the definite integral. When we use substitution to help evaluate a definite integral, definite integrals, remember, have bounds. You have a choice for how you handle the limits. You can do either of these things. I'll explain it. Whichever seems better to you. The important thing to remember is the original limits of integration were values of the original variable. In our case, mostly we use x. But when I substitute to u, they're no longer equal. U and x are not equivalent. You can solve the antiderivative as a side problem, translating back to x's, and then use the antiderivative with the original limits of integration. What that means is I solve it like I did here. First I solved it using u's, and then I turned it all back into x's. That's what the first thing they're talking about. I can solve the antiderivative and translate everything back to x's and use the original limits. Or I can change the limits of my integration, and then I don't have to substitute. Here we have a definite integral, and u is got to be equal to 3x minus 1. The derivative of u is equal to 3, and then just dx because the derivative of that is 3. Well, first let's divide both sides by 3. And that means I have du divided by 3 is equal to dx. Now I have two choices. I can either evaluate from x equals 0 to x equals 1 of this function, and this function is u to the 4th power. Dx is equal to du divided by 3, and I'm going to take that divided by 3 out in front of the integral and make it a 1/3. My other option is to change my limits of integration. For example, if I want to integrate this, well, I already know it's 1/3 u to the 4th du. That's not changing. But instead of saying x equal and 1 and x equals 0, I can just plug in up here. When x equals 0, u equals -1. And when x equals 1, u is equal to 2. I just plug it in. So I can change my limits from -1 to 2. Let me show you the difference. Here, 1/3. Using my power rule, this would be u to the 5th over 5, evaluated between x equals 0 and x equals 1. But I can't just plug it in. Now what I have to do is I can change this to u, which is 3x minus 1, to the 5th power, divided by 15, evaluated between 0 and 1. Now it's easy. I can do it because I'm back to x's. When I plug in 1 here, I get 3 minus 1, which is 2. 2 to the 5th is 32, divided by 15, minus, when I plug in 0 for x, I get minus 1 to the 5th, which is minus 1 over 15. The minus and the minus become a positive, and this is 33 over 15. And that would be my final answer. If I do it on the right, I have 1/3 u to the 5th over 5, evaluated between minus 1 and 2. And now this is equal to u to the 5th over 15, evaluated between -1 and 2, which is equal to 32 divided by 15 minus -1 divided by 15, which is exactly 33 divided by 15. So you can see that they are going to be equal, but these are just two different ways that I could do it. And that's basically what these two different ways are talking about. I can either use the original bounds, A, and turn everything back into x's and then put the values back, or I can solve using u and then solve for u, and then I don't have to translate that back to x. Last problem. First, we have to decide what we're going to use for u. And I know the derivative of the natural log is 1 over x, so I'm going to take a chance that u is equal to the natural log of x. That means du is equal to 1 over x dx, which means that dx is equal to x times du. I know I'm solving it different ways each time, but I'm trying to show you there are different ways. And I could probably solve it both ways. Let me see. This is equal to the integral. The natural log of x, we said, was u to the 6th divided by x, and we said dx is equal to x du. Notice my x's cancel. It has to. I can only have one variable. And now I get to decide, should I change my bounds or should I change everything back to x's in the end? It doesn't make a difference. I'll leave my bounds the same this time. So I go from x equals 2 to x equals 10. This is equal to, well, the integral from x equal 2 to x equals 10 of u to the 6th du, which is equal to u to the 7th over 7, evaluated between x equals 2 and x equals 10, plus some constant. And now I can turn u back into ln. So this is equal to ln of x to the 7th power divided by 7, evaluated between 2 and 10. Now I don't have to worry about saying x equals because everything's changed back to x. This is going to be equal to the natural log of 10 divided by 7 to the 7th power minus the natural log of 2 to the 7th power divided by 7. And we don't need the plus c anymore. And this is really just a calculator question. I'll put it in my calculator and tell you the answer. This equals 49.01. And that's it. Now, I took this was at the beginning of the chapter, and I thought it was too hard to explain. Now it's at the end of the chapter, so I'll try to go through it and see if it makes sense. And you could go through the problems again and check what I did. So the goal is to turn this composition of functions into a function of just u, where I could take the antiderivative of f of u. 1, let u be some part of the integrand. The integrand is the inside of the integral. A good first choice is one step inside the messiest bit. What that means is, notice in all the problems that we had, the messiest part was like ln of x, 3x minus 1. If it was just x to the 4th, we can easily take the derivative, but that makes it become more messy. We compute the derivative of u with respect to x, translate x's into u's, including the dx, and then when we're done, everything will be in u's. If we're doing just integration, we go back and substitute back the x's. If it's definite integrals, we need to make sure our bounds match the variable that we're using. And that's what all this says. I don't think that you would have understood it better at the beginning, but I wanted to include it here. And that's it. Thank you for watching, and I'll get the next video out to you as soon as I can. Have a good night.